So, last lecture we looked at something called uniform quasi-wideness, which was another view on the notion of nowhere denseness, which was a priori looks a bit quite different from nowhere denseness, but actually it turns out it is the same thing. So let me just remind you the definition here, because we will be using it throughout the whole lecture today. Essentially, today's lecture is devoted to applications of uniform quasi-wideness, both combinatorial and then algorithmic. So, the definition of uniform quasi-wideness is as follows, and I will draw a picture on the fly somewhere here. So, a class of graph C is uniformly quasi-wide if for every radius r that I wish for, as usual we are fixing some radius that we are concerned about, yes, there exists a constant SR. This is the number of vertices I will remove from the graph, and there exists a function NR from natural numbers to natural numbers, such that for every graph in my class, and for every subset of vertices of this graph, which is sufficiently large, of size at least nr of m, where m is also some parameter. So this is the number of vertices that I wish to find that are far from each other. Yes. There exists a subset of A called B, which is large in a sense of size at least m. Yes? And there exists a very small subset of vertices S, which is disjoint with B, and of size at most SR, yes, such that B is distance R independent in G minus S. So what's the intuition? The intuition, as we discussed it last week, is that if you've got a graph from a nowhere dense class, well, a sparse graph, then the intuition is that in a sparse graph there should be many vertices that are far from each other. Yeah? That's the basic intuition about sparsity. A sparse graph is like well spread. This is not necessarily true, because your graph might be simply a star. Yeah? Where every two vertices are close to each other, though a star for any reasonable definition of sparseness is a sparse graph. Yeah? But this is a little bit of a stupid example, because you can remove the center of the star and then the vertices are far from each other. Yeah? So this is exactly the formalization of this intuition. In a sparse graph, you should be able to find many vertices that are far from each other, yes, subject to maybe deleting a small number of vertices on the way. Yep. So to make it more formal, if I've got a graph from a class and I've got a large subset of vertices, this is A, yes, then I should be able to find in this subset of vertices a large subset B. So these blue vertices are B, yes? Such that the distance between every pair of vertices from B is larger than R. And this means distance are independent. Yeah? And to incorporate the fact that this should hold after deleting some hubs that govern through which the long distances in the graph, short distances in the graph are routed, yes, I allow removing a small subset of vertices S. So this is S, and the size of S is at most SR. And to say in a huge subset of vertices I might find many vertices that are far from each other, I do this quantification. I say that I wish for a set B of size at least M, yes, and then I need to start with a set A in which I want to find the set B that is of size at least sufficiently large, depending on n. And this sufficiently large is governed by this function nr, which is called the wideness of the class. Yes? Do you remember how it works? Good. So a few remarks. So the theorem that we proved during the last lecture is that C is nowhere dense in the usual sense that we had on the first lecture, if and only if C is uniformly quasi-wide. And today's lecture, we will capitalize on this theorem to prove some nice new results about nowhere dense classes using the characterization through uniform quasi-wideness. So two remarks were said about this theorem. Remark one is that the proof gives a p-time algorithm in the sense that given a graph from my class and a set A like that, I can emulate the proof and get the subset B and the subset S, yes, in polynomial time. Yeah. The second remark, which is somewhat surprising, is that this function nr of m is always a polynomial in M. In the sense that if a class is nowhere dense, then actually it is nowhere dense, it is uniform quasi-wide, with wideness function being, for a fixed class and fixed R, always a polynomial of M. Yeah, so this sufficiently large is actually not that bad. And we will use this remark during this lecture. We did not prove it, yes? Maybe on the next tutorial we will actually give a proof. We will see how it works. Good. So this is just a recap of what happened during the last lecture, and now today we will give a different characterization of nowhere denseness in similar spirit. So we will have a theorem looking more or less like that, and this characterization will be sort of in the spirit of nowhere denseness, of uniform quasi-wideness, but it will be a bit different. It will be a game theoretical definition of nowhere denseness. So I will define a game in a moment, and then we will prove that a class is nowhere dense if one of the players has a winning strategy on the class, in some sense. Okay, so the definition of the game is as follows. The game will be called the splitter game. The splitter game is played on a graph. So there is an arena that is a graph. This arena will change during the game, but at the beginning it is just a graph from my favorite class. And the splitter game has three parameters, so I will actually talk about L, M, R splitter game. And as usual, this will be the radius of the game. So essentially, I will always say something about the distance between two vertices at most R, yes, and this is the radius that we will be speaking about. L is the length of the game. So there will be an upper bound on how many rounds the game will be played. And M, maybe I'll call it budget. It is not really a parameter that is super important, as we will see during the tutorials, but yeah, you will see how it works. Okay, so there are two players in the game. One player is the splitter, and second player is connector. And the goal of this, so the game starts with the whole graph. The goal of the splitter is to get rid of the whole graph as quickly as possible within L rounds. So to arrive at an empty graph within at most L rounds. The goal of the connector is to prevent this. Yes? So if the splitter arrives at an empty graph within L rounds, she wins. and if the connector prevents this, is able to endure for L rounds, then she wins. Yes? So how the game is played? So round, let's say round I. So round I starts on an arena, which is a graph. It will be a subgraph of the original graph. Let's call it that the arena that we start with in round I is Gi minus 1. So G0 is actually the original graph G. Yeah, so when I start round number 1, I start with G0. I will end up with G1, which will be fed to the second round, and so on and so on. Yeah. So the arena of the game is Gi minus 1, and the game is as follows. So first, phase 1, connector picks a vertex. Let's call it Wi. So to draw it on the board, here is Gi minus 1, and the connector picks one vertex, say Wi. And then what the splitter does, splitter maybe, okay, after the connector picks the vertex, arena gets restricted to the distance R neighborhood of Wi. In the following sense, so this is like a localization step that the connector is forced to do. The connector needs to pick a vertex. Then we look at the ball of radius R around this vertex, and the whole rest of the graph is removed. Yeah? So I restrict the game to a radius R neighborhood of a vertex picked by the connector. But the connector gets to pick which one. Yeah? And then the second phase is that the splitter removes at most m vertices. Yeah, so what the splitter can do, she can remove this vertex, this vertex, this vertex. She can also remove the Wi that was picked by the connector. Maybe I will call it really not Wi but Ui, because just to be consistent with the nodes, let this set of vertices removed be called Wi, capital Wi. Yes? So then the arena, after these two phases, is the graph Gi, which is the neighborhood of radius R of Ui. Yes? More precisely, the subgraph induced in Gi minus 1 by this, and then I remove this Wi. And this is the next arena, Gi. And then the game proceeds to the next round, and as I said, splitter wins at some point if the arena gets empty. And connector wins if she is able to endure for L rounds. Is the game clear? So there are two steps here. One step is a forced localization step, where the connector needs to sort of restrict the arena to something that is small, yes, that is of radius R, and then splitter gets a move of like shattering this new graph using by deletion of a small number of vertices. Yeah? So this sort of corresponds to the intuition behind uniform quasi-wideness, that there is a localization that is hidden by these vertices being far from each other in a sense, yes? And there is this idea of removing the hubs there, which is encompassed by the set F here, there, and by removing a constant number of vertices here. Yeah? That's the intuition. Yes?
But don't you then look at the whole graph again, or you have forgotten completely?
I have forgotten completely the whole graph, apart from GI. So the next round starts with arena GI, which is like that. Yeah, so in particular the distances, yes, in the next round, in this, where I say radius R, here, these distances are in the arena. Yes? So the distances actually change during the game. Good, thanks. Okay, so now we will prove a theorem, somehow mimicking the theorem there, that C is nowhere dense if and only if for every radius R there exists length of the game and the budget to delete such that splitter wins the LMR game on any graph G from my class. In the following sense, so there is some, for every R, there is a bound on the length of the game and on the budget for the number of vertices that are being removed, such that on every graph from my class, the splitter can win. Yes? Is this clear? Sort of. And then this is actually equivalent to nowhere dense. Okay, so as usual in such theorems, we have two implications to prove. Okay? So I will start with the more difficult implication. So maybe this will be a little bit cryptic lemma. The cryptic lemma will say that this implication holds. Yeah, so if C is nowhere dense, then I have a strategy for the splitter. By the way, formally I should define what is a strategy, yes? But you can probably believe what is a strategy. A strategy is a function that, given the previous moves, returns the next move. Yep. I will only think about deterministic strategies. So to prove this, I need to give a strategy for the splitter for some bounded number of rounds. This will take me some space, so I will move to this board and wipe it. I hope that you already remember what is uniform quasi-wideness. So I need to show you the strategy. Yes. So here is my graph. So let's say that splitter has the connector has the first move, which is some node U1. So here is connector, here is splitter. Here will be his answers. So connector plays U1. Then splitter just deletes U1. Yes? Then connector picks some U2. Yes? This is U2, which should be, because the game was restricted to a ball of radius R around U1, this U2 should be at distance at most R, yes, in the original graph G0, yeah, from U1. So what splitter will do, she will remove U2 plus a path of length at most R in G0 to U1. Yes? So she will remove this vertex, plus she will remove also some path of length at most R here. I did not specify the length of the game nor the budget so far. I will specify it later. I need to first give you the strategy, and then from the strategy it will be clear what should be the length and the budget. Okay, so the next round connector picks some u3. Okay, so the game got restricted to some ball of radius r around u2. Here is some u3. So again, splitter removes u3 plus a path of length at most r in G1 to U2. Yes? Because when U2 was picked in G1, yes, then the arena got restricted to a ball of radius r, which means that in G1 there was a path of length r to U2. And I will also remove, similar to the first step, a path to U1. So I also remove a path of length at most r in G0 to U1.
From U3.
From U3. Of length from U3 to U1. Okay, note here that for this second path, this is a path that existed in G0. Yes? Maybe when I was restricting then the arena to G1, some of the vertices of those paths got removed. But it is even better, meaning they are already removed. Yeah, so if some of the vertices of this path got removed already before, there is no need for the splitter to remove them. So I hope that you can sort of see what will happen later on. So in general, what do I remove as a splitter? I remove in round I remove ui, plus for every j smaller than I remove a path of length, I will call it pji. This is a path of length at most r from ui to uj in the graph gj minus 1, in the arena where uj was selected. So that's a strategy. I did not say what is the budget that this strategy obeys, but the lemma that we will prove is that using this strategy, splitter wins in at most an r of, and actually 2r as far as I remember, of 2sr plus s2r plus 2 rounds. And so, more precisely, C is nowhere dense, which implies that C is uniformly quasi-wide by the theorem that was here, yes? Which means that there exists some number s to r and function n to r, which govern this uniform quasi-wideness for the radius to r. So I claim that this bound on the number of rounds is sufficient for the splitter to win using this strategy. So what I will write is that the number of rounds that I allow splitter to use is exactly that. Yeah, but I will just write s instead of this s to r. While m, the budget that I allow splitter to remove at every step is, well, at every step I remove one vertex plus paths to all the previous ones. Yes, and the paths are short, of length at most r. So maybe I'll write that I remove like one vertex plus for each of the previous guys, and there are that many of them, I remove at most r plus one vertex. Actually, at most r because I already removed the beginning. Yeah? So this is the budget for the deletions that I allow for the splitter. so this lemma shows that splitter wins LMR game for these values of LMR. Okay, so now this is something to prove. So let's call this lemma, I don't know, lemma star, as we move here to proving lemma star. So, how the game actually proceeds? Maybe I'll just draw it. There is this first vertex U1 picked by the so here is the initial arena. Here is the first vertex U1 that is picked by the connector, and the arena gets restricted. So this is G0. It gets restricted to some graph G1. Yes. Actually, this restriction is very small. It is just the removal of this vertex. Yeah. Then there is U2 that is picked. Yes. I have then some path. Path looks like that. Yes, that gets removed. And here is G2. Note that this graph G2 is now disjoint from this path, P12, because this path got explicitly removed. Yeah. Now I've got U3 here, and well, there is some path to here, there is some path to here, drawn like that, and these two paths are removed, so the next arena, G3, is completely disjoint from them. Yes? And so on. U4, U5, U some capital M, where M is this uniform quasi-wideness bound. Now, this is a general principle of working with lower dense classes. If you have a large set of vertices and you don't know how it looks, how it works, and so on, you just hit it with uniform quasi-wideness to dig some structure. So we've got a large set of vertices, so we assume that the play is long, yes, that the splitter did not win within this number of rows. So we assume that the play is long up to m steps, so we've got a large set of vertices U1, U2, and so on. We hit it with uniform quasi-wideness. What does it give us? It gives us some U, say, I1, U, I2, and so on, U, I2, S plus 2. These are vertices, moves of the connector, such that they are distance 2r independent. Sorry, 2r? Let me just check the notes. I was stupid. Actually, I need just uniform quasi-wideness for radius r. I'm sorry. Here is S, of course. Yeah, I'm sorry. It should be uniform quasi-wideness for radius r. This is even better, right? Meaning this is a smaller number. I got confused because in the second proof that we are going to do today, we'll use actually uniform quasi-wideness for radius to r. Okay, so these guys are distance r independent. Yeah, they are pairwise at distance more than r. Let's say that this u I1 is smaller than I2, and so on, smaller than I2 S plus 2. So essentially, we have highlighted some moves of the connector such that they are far from each other in the graph G with some set S removed. And the set S is of size at most S. So I removed some vertices in the graph such that these guys, after this removal, are far from each other. Yeah?
Here you use basically the no-wide entrance.
The uniform quasi-wideness. Yes, here I use uniform quasi-wideness. I've got a large set of vertices. I hit it with uniform quasi-wideness. I get a large set of vertices that are far from each other.
But you don't know that originally that the paths are the only paths. You didn't know that in the beginning, right?
I didn't understand.
The paths you removed.
Yeah, the paths I removed,
Yes,
meaning they are not in this argument so far.
They could not, I think.
Yeah, they may be hit by those guys. Yeah, but the intuition is that the number of those guys is bounded by S. They're small number of vertices. The intuition is that they will not be able to hit all those paths. And this is what we are going to show now. Okay, so I've got those S2, S plus 2 vertices, so I can then group them into pairs. So here, maybe I can extend this, this picture a bit to make it clearer. So here are some more vertices in this game. Maybe this one was picked as well. This one, and this one. Yes, so there are 2 S plus 2 of them picked. So now let's look at this guy and the second one. The first and the second. So when I was removing as a splitter, when I was removing this vertex together with some paths, yes, I have removed a path of length at most r connecting U4 with U2, yes, that was entirely contained in this graph G1. Yeah? So this path is completely disjoint from everything else that was done later on. Okay, let me look at the second pair, so U5 and U10. Again, here there is a path between U5 and U10 that is entirely contained after the removal from the previous pair, yes, and is completely disjoint from everything that was later on. So this pair U5, U10 is contained in the graph G4, yes, which in turn is then disjoint from this previous path I chose. So again, I've got here a path of length at most r between this guy and this guy. And again, like here have a path like that, and here I have a path like that. And all these paths are pairwise disjoint. So then claim that I have is that paths P I to j, say I to j minus 1, I to j, these paths are pairwise disjoint. That's because each of those paths was selected in a graph in the arena after the removal of the previous ones and gets removed, so it is disjoint with the later ones. But there are S plus 1 of them, and S can hit at most S of them. Yeah? So my set S that I removed to get this distance R independent set, it may hit this path, maybe it will hit this path, maybe it will hit this path, but at least one of them will be free. And this is a contradiction. Because these vertices should have been at distance more than r from each other after the removal of S. Okay. So in this way, we have shown, and this is like a very classical example, that if some process works for too many steps, it creates a structure in your graph that is large, that you can hit with uniform quasi-wideness and get a contradiction. And therefore the process, the game, should finish after a bounded number of rounds. Okay, so this was proof of one direction. So now let me prove the second direction. As usual, this will be easy. So the lemma in the other direction works as follows, that I need to prove that if C is somewhere dense, then there exists a radius r such that splitter wins such that for every length of the game and budget, connector can win the LMR game on some graph from my class. Yep, this is the contrapositive of the second implication. I need to prove that if my graph is not nowhere dense, it is somewhere dense, then actually I have a suitable strategy for the connector. Okay, so as usual, this is easy. Actually, there exists an R. Yeah. So if C is somewhere dense, then for some R, I've got all cliques as depth R minors. Yeah, so for every clique that I wish for, say of size 1000, there will be a graph in my class that contains this clique as a depth R minor. Okay, I will prove that if G contains KT for t equal to, I think, Ln plus 1 as depth 3R plus 1 minor, then connector wins. Wins in LM 3R plus 1 game on G. Sorry, it should be, it contains KT as a depth R minor, then the connector wins the game with slightly larger radius. Yeah? So the logic of this proof is that if the class is somewhere dense, then for some R I see all the cliques as depth R minors, and then on these cliques the connector has a strategy for the game LM, for any LM I wish for, and radius 3R plus 1. So actually in here there exists an R, this R will be actually 3R plus 1, where R is this depth at which I see all the cliques. And this, so this is claim. And the proof of this claim is actually showing a strategy on the picture. So here is my graph G that contains this KT as this shallow minor. So what does it mean contains KT as a depth R minor? It means that here I've got those branches, those blocks that are pairwise disjoint and pairwise adjacent to each other, and each of them has radius R at most. And they're pairwise adjacent. This means that KT is a depth R minor. So now the connector plays. The first move is to pick any branch set and pick its center. So observe now that every other vertex within the blue blocks is at distance 3R plus 1 from the center, because I can always travel by radius R within this blob to the connection point to any other blob I wish for, and then within distance 2R I can go to the center of this blob and to any other vertex. Yes? So by choosing center of any blob, this localization step, restriction to the radius 3R plus 1 around this vertex, in this step all the blue blobs are still there. No? Okay, so now the splitter gets her move. So she can remove at most R vertices, M vertices from the graph. Yeah? But by removing M vertices from the graph, she can spoil at most m of the branches. All the other branches that are not spoiled, yes, they remain free and they remain a depth r minor of a clique. That is by m smaller. And then again, the connector may pick any center of any branch set, and the clique is preserved. And the only thing that the splitter can do now is fall again at most m of the branches. And so on and so on. Yeah? So the strategy is always pick a center of an you write it like this, spoiled? Hopefully this is grammatically correct. Of an unspoiled branch. So if the connector uses this strategy, then after L rounds, there will be still at least one branch that will not be spoiled. Yeah. And she wins then, yeah, because the graph is not empty. So this was actually easy. Usually those proofs are easy because you get a clique, which is a very rigid structure, a very well understood structure, and you just show that this clique is robust enough to give, in this case, a strategy for as many rounds as you want. Good. Okay, so this was the splitter game. Historically, it was introduced as one of the tools for proving first-order model checking algorithm on lower dense classes. So 2 weeks ago, we were talking about this bound expansion, first-order model checking, and I said that instead of doing linear time on bound expansion, you can get almost linear time algorithm for lower dense classes via completely different methods. And this is one of the technical tools that is used there. So essentially, the whole algorithm works as a recursion using the strategy for the splitter here. A very high level. Though, admittedly, there are not so many other usages of this game. I've seen a few where it is more convenient to think in terms of splitter game rather than uniform quasi-wideness. But my personal intuition is that usually uniform quasi-wideness is a simpler tool to apply than splitter game. But it is also useful to know this because it gives a lot of intuition about what is the structure in lower dense classes. Because you can see the structure as this alternation of this localization and deletion steps. Good. So this was splitter game, and we are halfway through the lecture. And now we can move to the second part, namely algorithmic applications. And for the algorithmic applications, we will concentrate on our favorite problem in sparsity. Actually, we have two favorite problems in sparsity, but one is a little bit more favorite than the other. And the problem is distance R dominating. So given a graph, I would like to check whether there exists, okay, maybe I can write. So given a graph G and an integer K, check whether there is a distance R dominating set of size at most K. Yeah? Whether I can dominate the whole graph using at most K vertices, where domination means that every vertex dominates itself and all the vertices in ball of radius R around it. Yeah? So I will write it concisely as follows, that I will just write that dom R of G is at most K, where dom R of G is the smallest size of a distance R dominating set. It will be also convenient to use the following notation, so this is the same, that for a subset of vertices A, I can define this number dom R of GA. So this is the smallest size of a set that distance R dominates at least this A. Yeah? So if I care only about dominating some subset of vertices A, then I write it like this, dom R of G and A inside. So the dom R of G is just dom R of G and the whole vertex. So now we are thinking about this distance R dominating set problem in this decision version, where I'm given a number k, and I would like to check whether there exists a solution of size at most k. So if you see this version and you have attended the course parameterized complexity, you might start thinking about, well, there is this number k, there is this distance r, maybe these are reasonable parameters to look at. So our goal, now in, say, unparameterized terms, is that to find algorithms that work, that are efficient for small r and k. Actually, I will consider r constant, as we usually do in sparsity. K will be the parameter. So to get it more precise, I would like to, my goal is the following running time, some function of the parameter k, the number of vertices I'm allowed to pick to the independent set, times the size of the graph n to some fixed constant. This is a constant, and this should be any function. It can be exponential, because the problem in general is NP-hard, yeah? So I cannot aim for a truly polynomial time algorithm, yes? I need to have some exponential blow-up somewhere, and I would like this exponential blow-up to be confined in this parametric factor of the running time. And, yes?
The constant can depend on R.
The constant C can, like, in the setting as I phrase it, where I say R is a constant, then formally it can depend on R, but actually this will be a universal constant. It will not depend neither on R nor on C. It will be just, I think it will be actually 2, meaning it will be a quadratic time algorithm. During the tutorials we will work out a linear time algorithm, so this will be actually equal to even 1 later on. And if you have attended parameterized complexity, you have probably seen this kind of running time a lot. So this kind of running time is called FPT for fixed parameter tractable. Yeah. And the intuition is that the algorithm works efficiently whenever k is small. Okay, so that's our goal.
And does R not appear here?
R is considered a constant for fixed R. So what will happen is that this function f, yes, this is a function which will depend on C and R. So there will be some constants hidden in the function that will heavily depend on C and R.
But
Yep.
actually, since C doesn't depend on R, we don't have to assume that R is constant.
Yeah, we don't have to assume.
But we always do. So.
But we always do, and just for the sake of aesthetics, I will consider R a constant. But indeed, this will be actually an FPT algorithm parameterized by both R and K. There might be some caveats with like R being not fixed, whether this NR that I will use in uniform quasi-wideness is computable or not. So there are some computability issues inside, but they are of meaning they are minor issues and rather technical. So I'd rather sweep them under the carpet. Good. So that's the goal. And now let me give you a strategy for achieving this goal. So the general intuition with working with dominating set problem is that every vertex U, has two roles. In a dominating set problem, it has always two roles. First, it can be a dominator. In the sense, it can be taken to a dominating set so that it is able to dominate some vertices around. And second, it imposes a constraint that it needs to be dominated. So I will call it that it is a dominatee. So the idea is that we have those two roles, and we will actually separate them. In the sense that I will think about vertices that are essential for being dominators, and vertices that are essential for being dominatees, and I will try to reduce their number separately. So this will become clear later on. So the two roles are dominator and dominatee. And in the algorithm that I will present now, the idea will be that I will reduce the number of vertices for which this role is essential. So I will reduce the number of vertices for which I need them to be dominated. So this will become clear later on when I define this more formally. So I will say that a subset of vertices Z in my graph is a distance R, subset of vertices R, distance R, domination core for G and some parameter K, if now this is a little bit might be a little bit confusing, but every set B that of size at most K that distance R dominates Z, actually distance R dominates V of G. So all the vertices. So this is a set of vertices such that for every candidate dominating set, so a set of size at most K, if those vertices from the core are already dominated, then automatically the whole graph is dominated. Needs to be dominated. So do you see any example core that is always there in the graph? Yeah, so example. Z equal to the whole graph, of course, is always a domination R core. Distance R domination core. Yeah? But we will be interested in finding a distance R domination core that will be small. And we'll prove it. So the slightly surprising lemma that we will prove is as follows. So lemma, so suppose that G belongs to a class C, yes, R is fixed, and C is, already I will write, is uniformly quasi-wide with those margins as R and functions, wideness functions and R's. And say that Z is some subset of vertices, and Z is large. It's of size at least n to R of K plus 1 times, I will just check it so that I do not mix something later on. R plus 1 to the power S to R plus 1. Yeah, some number. Yes? This is a large number that depends on K, R, and, well, depends on K and R and the class itself. Yeah? So sufficiently large depending on k. Then there is z from z such that for every d subset of vertices of size at most k, d distance r dominates z if and only if the distance r dominates z minus z. So this is a lemma that gives you a so-called irrelevant dominatee. If I have a large set of vertices, depending on k, then I can always find there as a vertex such that its domination is being forced by the domination of the other guys. For every set of vertices, if those vertices, those k vertices dominate all the other guys, then they also dominate z. Yeah? And moreover, z can be computed in p time. So this is a lemma that I will prove, but before proving it, a trivial corollary is that there is always a domination core, under the supposition of this lemma, a distance r domination core of size, well, at most this. Actually, smaller than this. Why? Because I can start with the whole vertex set, which is a domination core. I can apply this lemma, find an irrelevant dominatee, remove it from my core. And this equivalence tells me that removing an irrelevant dominatee from a core preserves the core. Yeah, because this implication exactly tells me if the core gets dominated after the removal, then this additional vertex is automatically dominated as well. Yeah? So I remove the first vertex from the core. I apply the lemma again, I remove the second vertex from the core. And so on and so on and so on. I do at most n steps, and I arrive at a core of size at most that, for which I cannot apply my lemma any longer. Yeah? So this is like an iterative removal of irrelevant dominatees. Okay, so we are left with proving the lemma. So, again, the same principle. I've got a graph, G, from a class that is uniformly quasi-wide, with some margins and wideness. And I've got a large subset of vertices, Z, and I would like to find some vertex inside that is an irrelevant dominatee, in this sense. If I have a large set of vertices that I do not really understand, what do I do? You apply uniform quasi-wideness, especially since the lower bound on its size is expressed in uniform quasi-wideness terms. Yeah? So, from the uniform quasi-wideness, I have a set B, subset of Z. Size of B is at least what? This funny number that is there. K plus 1 times r plus 1 to the power s2r plus 1, such that B is distance 2r independent in G minus S, where S is a subset of vertices of size at most S2R. Yeah, so here I removed some small set of vertices S, so that at the end of the day, after removal, I've got many vertices, that many vertices B, that are distance 2r, distance more than 2r from each other, which means that balls of radius r around them are disjoint. This is exactly being 2r independent. Right, so B is that large. So the next step, and this is also a step that is very commonly used in conjunction with uniform quasi-wideness, is that I classify B with respect to profiles on S. So every vertex of B, for every vertex of B, I look at the distance to the first vertex of S, to the second vertex of S, to the third vertex of S, and so on. But I think of those distances up to threshold R. So I record that I am at distance 5 from this guy, maybe I am distance at 10 from this guy, and I am at distance more than R from this guy, which I will write as infinity. Yes? So how many profiles there are on the set S? The number of profiles, distance R profiles, is at most, what? R plus 1 to the power S to R. Yeah, because they are at distance 1, 2, 3, 4, up to R infinity. Which means that there is a B prime containing B of size. Now we apply pigeonhole principle, yes? Because B is of this size. So it is larger than k plus 1 times this. So there is a size k plus 2 subset of vertices such that B prime has same profile on S. Yeah, is it clear? So again, a filtering step with respect to the profiles on S. Okay, now my claim, maybe I will highlight them somehow. So maybe this guy, and this guy, and this guy, and this guy, and maybe this guy, they are in my set B prime. They have the same profile on S. So my claim is that any Z from B prime is actually an irrelevant dominating. In this sense, if I am able to dominate everybody from Z apart from this Z, then I dominate Z as well, by a set of size at most k. And so what we need to prove is that if D is a set of size at most k, and D distance R dominates Z minus Z, then D dominates Z as well. Yep, it's clear? Because in this equivalence, this implication always holds. This is trivial. It's just domination of a smaller thing. And here I need to prove that domination of this also forces domination of this small Z. Good. So where should I do this? I think perhaps I will just squeeze the rest of the proof in this rectangle. Okay, so suppose that there is such a D. Yes? So how does D looks like? This D maybe have a vertex here, has a vertex here, has a vertex here, and so on. if distance R dominates all the vertices of Z minus Z, maybe this Z is here. This is the guy Z. Yes, and I would like to prove that it is dominated this way. So note that D intersects at most K balls N are in G minus S around the vertices from B prime. I've got those vertices from B prime, here, 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 here. There are K plus 2 of them, B prime minus Z. Yeah? There are K plus 2 of them. One of them is the Z I'm concerned about. Apart from it, I've got K plus 1 vertices. And these balls, after the removal of S, they are disjoint. Set D has at most K vertices. So it can intersect at maybe this ball it intersects, maybe that ball, but one of them will be free from D. Yeah? So this means, but D, distance R, dominates all of B prime minus Z. Yeah? Because it dominates everybody from Z minus Z, so in particular all those vertices. So how the hell did this vertex got dominated by D if there's nobody in the ball of radius R around it from my dominating set? Well, it was a ball in G minus F, yeah? There is also a possibility that there was some vertex D from D, yeah, that dominated this guy via a path of length at most R that crosses S. This is the only possibility. Yeah, so there is D from D that dominates this this B from B prime minus Z via S. Yeah? But now kicks in this idea of classifying according to profiles. Yeah? This vertex that here has the same profile on S as this vertex B here. This distance is the same as this distance. Yeah? So now we see this vertex D can go to this vertex of S and then follow this path to dominate Z as well. So D dominates Z as well. And we are done. Is this clear? What happened? Yeah? We found many vertices that behave in the same way with respect to S, and the fact that there are many vertices, and we care about domination by a small set of vertices, D, means that one of them needed to be dominated through those hubs, through S. But domination through S automatically dominates all the vertices with the same behavior on S. That's what happened conceptually in this proof. Good. Okay, so we have proved this lemma, even though it is already wiped out a little bit. But in particular, we have proved this corollary that there is always a domination core of size bounded by some function of k only. I will call it g of k, and just write it down that this g of k was this amazing number. And to r, k plus 1, r plus 1 to the power s plus 1. S to r. Yeah. So now we have reduced the number of dominatees, people essential for being dominated, to a function of k only. And to get a parameterized algorithm, this is actually already very easy. So maybe I can phrase it as a lemma. So this we don't need anymore. So the lemma will say as follows. So given G and Z, K and R, we can check whether I can dominate Z in G, distance R dominate, using as most K vertices in time. Oh, well, I will do it brute force. 2 to the size of Z times K times poly of the size of the graph. Yeah? Note that now this running time will be like a function of K times a fixed polynomial. Maybe I can write it as n power c to be compliant with how we denoted it before. Yeah? So now if I apply this lemma on this domination core that is of size bounded by a function of k, this will be just a function of k. Yeah? And the proof is very easy. So if I have my graph and I care only about the domination of a small domination core Z, the only thing I care about is, can I cover Z with at most k distance R neighborhoods in Z. Yeah? Every vertex of my graph U, it has some distance R neighborhood in Z, which is Z intersection with the ball of radius R around U. And these are the vertices that it dominates. And two vertices with the same neighborhood, they dominate the same thing. Yeah? I need to care only about one of them. So what I compute this family F of all distance R neighborhoods in Z. Then this family has size at most 2 to the size of Z. Yeah? And we brute force all k tuples from F. Brute force, I mean, I check whether there is a k tuple of vertices of sets from F that covers the whole set. Yeah? So then computation of this family F takes polynomial time because it just boils down to running a BFS from every vertex. Yes? Then this family has this size, and this is the number of tuples of size k of neighborhoods. Yeah? So by taking this corollary and this lemma, we get the following theorem for every lower than C and R that is fixed, the distance R dominating set on C can be solved in time some function of k times a fixed polynomial, which was exactly what I promised in the beginning. In polynomial time, I compute a small domination core, and then I brute force the core. Okay, so this is the theorem I wanted to mainly prove today. Let's see at this function f. Let's take a closer look at this function f, because if you have attended pointers algebra, you probably know that we usually care of the asymptotics of this function f. So a priori, this function f depends on the size of the core, which is this horrible number depending on uniform quasi-wideness. But at some point, I told you that actually this uniform quasi-wideness number are not that bad. Yeah, they are polynomial in this. So for fixed R, this is linear in K. So this whole number G of K is actually polynomial in K. then when we apply this lemma, a priori, we get running time 2 to the g of k times a polynomial factor. But observe that I did really brute force here. In the sense I just said the number of all the neighborhoods in Z is at most 2 to the Z. But then, so polynomial uniform quasi-wideness implies this. But on the other hand, I have this neighborhood complexity which tells me that at least in boundary expansion classes, the number of different neighborhoods, distance R neighborhoods on Z will be linear in Z rather than exponential. And in lower dense, it will be almost linear. It will be like Z to power 1 plus epsilon. Yeah? So then instead of writing 2 to the Z to the power K, I'd rather write Z to power 1 plus epsilon to power K, which suddenly becomes K to order of 1, because g of k is polynomial in k, to the power k, which is 2 to the order k log k. Yes? Which means that the algorithm runs in time 2 to the order of k log k times polynomial in the input size. Which is, as far as a parameterized algorithm go, not that better running time. Meaning I've seen much worse. And of course, in this O notation, there is a huge factor that depends on the uniform quasi-wideness, that depends on this O of 1, which is pretty bad. But still, it is a constant, depending only on the class and the radius. Yeah? So in this running time, this depends badly on R, yeah? But on K, it behaves not so bad. Okay, so in the remaining 10 minutes, I would like to strengthen this result, this theorem that we proved. So this is a parameterized algorithm for the problem, an SPT algorithm. And if you attend this parameterized complexity class, you have probably also seen something called kernelization. So kernelization is a kernelization algorithm is an algorithm that really works in polynomial time, and it reduces the size of the input structure, the input graph in this case, to a size that is bounded only by a function of parameter. So in this case, k. So in some sense, already our lemma about domination core is like a partial kernelization, because it reduces the number of dominatees to a function of k only. Yeah? But still the graph can be large. So to get a kernel for the problem that I will define in a moment, we also need to reduce the number of dominators. And this will be quite easy. So formally, the statement that I would like to prove, theorem, is that there is, okay, so C is nowhere dense, R is fixed. So then there is a function, how to call it, P. Yeah? And a p-time algorithm that does the following. So it gets an instance, say gk. So this is an instance of distance r dom set, where G belongs to my class C. Yeah, so this is like previously, but now it should work in polynomial time. Yes, and it will also output some H, which will be an induced subgraph of G, and K as well, such that the domination number of G is at most K, if and only if I will also need a subset of vertices Z. So the domination number of G is at most K if and only if in H I can dominate Z with at most K vertices, and the number of vertices of H is at most P of K. So in a sense, I take an instance of a distance R dominating set, I transform it in polynomial time to an instance of distance R dominating set, well, with some annotations, in the sense that I have only some subset of vertices that needs to be dominated. These instances are equivalent in this sense. So this has a solution if and only if this has a solution. But this instance is of size bounded by a function of K only. Is this clear? What happened? So due to lack of time, I will sort of sketch the proof of this, but I hope that it will be clear what happens in this theorem. So we have already observed that we can compute some domination core that is small. So first of all, compute distance R domination core for G and K. And this is Z, and the size of Z is at most G of K. Is everything clear? Yeah. So I compute a small domination core. Yeah? So far the graph looks like that. That I got my huge graph G. I did not remove any vertices so far. And I've got the small domination core Z here, which is already small. Yes? Now I need to remove the rest of the graph. But observe that, again, this is the same observation. If I have here a vertex U, and here a vertex U prime, which have exactly the same neighborhood in Z, they dominate the same thing. So I don't need both of them. I just need one. So the idea is that for every neighborhood in Z, for every possible neighborhood in Z, I will just preserve one vertex with this neighborhood. So for every distance R neighborhood in Z, let's call this neighborhood maybe L, preserve, or maybe mark, one U belonging to with exactly this neighborhood, being the radius R ball around U intersection Z. Yes? But it's not only that I need to preserve this guy, I also need to preserve the paths that witness that. Yeah? Plus paths to L, from U to L, that witness that. Yeah? So let H be the subgraph induced by marked vertices. Yeah? So what's the size of H? Like maybe brute force. Well, first of all, I need to mark Z. Subgraph reduced by the marked vertices plus Z. Yeah? So I need to, I have Z marked explicitly. Plus, for every neighborhood on Z, and there are at most 2 to the G of K possible neighborhoods, I marked one vertex. Plus, to every vertex of Z, I may mark a path of length at most R. So 2 to the G of K times G of K times R plus 1, I guess. Which is a function of K only. And now a claim that I will not prove, but I hope that you are able to do this symbol pushing yourself, is that G has a dominating set of sizes most k, if and only if it is possible to dominate Z in G by at most k vertices. This follows immediately from the fact that Z is a core. Yeah? And this is equivalent to the statement that in H it is possible to dominate Z using at most k vertices. And that's exactly the intuition here, yeah? Meaning if I have a dominating set here, then it is trivially a dominating set like that, but because this is an induced subgraph. And if I have a dominating set here, then I just move the vertex to the representative that got marked, and this is a dominating set that witnesses that. Yeah? I hope that you believe me. And yes, we are done. This is a function of k only. So that's the end of the proof of this theorem. And again, you can consider what should be the function p of k. And again, the same story. G of k is actually a polynomial in k. And instead of writing 2 to the g of k, I could have written the number of neighborhoods, which is actually something like g of k to 1 plus epsilon. So polynomial in g of k, which is a polynomial in k. So actually, then, I've got this remark that p of k is a polynomial in k. Yeah? So we actually obtained in this way a polynomial kernel for distance R dominating set on any lower dense class. And another remark is that you can strengthen this theorem. So there is a linear kernel in bounded expansion classes and almost linear in lower dense classes. Yeah? So you can prove this theorem, exactly the statement, but with p of k being linear in k in bounded expansion classes and almost linear like k to 1 plus epsilon in lower dense. So this proof is more difficult than what we have shown today. It sort of follows the same idea of removing the dominatees and then removing dominators at once at the end, but you need to work much more. We actually have all the tools that are needed there. In the sense like you use neighborhood complexity, you use uniform quasi-wideness, you use recoloring numbers, you use essentially the whole arsenal that we have prepared. During this year's edition of the course, we decided not to give the proof of this theorem, of this remark. We gave it the last time, like 2 years ago. So if you are interested, you can see the proof in the notes from 2 years ago. It would take us another lecture to do this. Meaning it is conceptually not that difficult in the sense of the toolbox that we need, but there are several steps that you need to do, and this is not a really easy result. It took us some time to get it. Okay, so I hope that that this clarifies the application of uniform quasi-wideness. We will use it later on as well. And yeah, thanks for the lecture, and we meet each other in half an hour for the tutorials.